This is the second part of our discussion on Chapter 1. In this video, we're going to discuss significant figures and dimensional analysis. Alright, we're going to move on to a new subject, significant figures. I'm hoping that you've heard about significant figures before, that you know how to use them, and so this will be easy for you. But if you haven't, or it's been a long time, then these are going to be important for us. Significant figures are often pronounced sig figs. It can help with understanding to consider examples of things that are not significant figures. So we're going to consider three primary examples. The first are known as leading zeros. Here I have a few examples, and we're going to go through and figure out how many sig figs each value represents. In the first one, the leading zeros are starting from the left, moving to the right, and any zero until you hit the first non-zero number. So there's our first non-zero, and then after that we have another non-zero. This would represent, so here we have leading zeros, so this would just represent two sig figs. In the second example, there's one leading zero, and we have our first non-zero value. The rule is, though, that zeros in between non-zero values are considered significant. So in this number, we'd have a total of 1, 2, 3, 4, 5, 6 sig figs. Okay, in the third example, the inclusion of a decimal point can affect significant figures, but the rule is still the same if the zeros are all to the left of the first non-zero value. So in this case, that would be our non-zero value. So these would all be considered not significant. So this would only have one sig fig. All right, in the last example, again, the decimal place can have meaning for significance, but not if all the zeros are to the left. So those are all not significant. We're left with 3. Okay, the second example are trailing zeros. So let's go through a few more situations. So in this case, the trailing zeros are the ones that come after or to the right of the non-zero values. So here we have 3 trailing zeros. So the convention says that those are not significant, and we're left with 2 sig figs. In the second example, even though I have a lot more zeros, they're still all trailing, and so those would not be significant. Cross this out. There is only 1 sig fig in this example. Okay, in the third example, this is somewhat similar to the previous slide. Zeros that are in between non-zero values, those are considered significant. And then this leaves us with just 1 trailing zero. So here we'd have 1, 2, 3, 4, 5 sig figs. All right, the last one's where you want to pay close attention. When you include a decimal point in a problem, zeros that are to the right of the decimal point are supposed to be significant. So in this example, all of those would be considered significant. So we would have 1, 2, 3, 4, 5. Okay, so that's the convention for trailing zeros. Now I do have one issue that I've never liked about the convention. Let's go back up to our first example. What if this 0 right here was significant, meaning when the measurement was taken, we knew for sure that that was supposed to be 0. So that's what we mean by significance. There's precision there that we are confident in. Well, how would we represent 22,000 and still show that that 100th spot is significant? The convention says that we can't show that. So there are other options. In fact, this is maybe the better option to go with by default. It's known as scientific notation. So I'm assuming that you've seen scientific notation before, so I'm just going to cover it quickly. It's the one that uses powers of 10. So in this example, let's go ahead and convert these to scientific notation. I've actually gotten really good at all these decimal places lately because I've been working with my 5-year-old daughter, and this is, my daughter who's in 5th grade, and this is some of the math that they go through. So here we have our tenths, hundredths, thousandths, ones. What I'm getting at is, as you know, each decimal place that I move is a power of 10. So when writing scientific notation, the standard is to leave the decimal after the first non-zero value. So in this case, I would write as 204, and then I multiply it by the power of 10 that I had to use to get there. In this case, I moved the decimal. Let's go back here. Okay, in this place, I had to go to the right. So here I'm negative 10 to the minus 2. That would be my scientific notation for that. Now, technically, I can write it like this if I want, or some other version of that. But normally, you would see it with just the decimal after the first non-zero value. Okay, second example here. So even though there's no decimal shown, it's implied that it's right there. So to reach that standard position, we've gone over 5 values. So 5 powers of 10. So here we would write this as 7.043. Now that is assuming that the trailing zeros in this case were not significant, which our standard tells us. But what if we knew that this value right here, get rid of that, what if I knew that that was significant, it really was supposed to be 0? Then scientific notation, because I'm using a decimal place now, I would add that 0 there and complete that with 10 to the 5. All right, so that's why scientific notation is nice, because it uses the decimal place by default, and so you can you always know that any trailing zeros must be significant. All right, to finish this off, okay, and then on the last one, again, this kind of goes back. The convention says that because this had a decimal place, then all of these should have been assumed to be significant. So we'll go ahead and keep that assumption. Say we have 1.40000 now. And I had to move my decimal place 3 spaces, so I would be 10 to the 3. Here's our last example of something that's not significant, what I'm calling spurious digits. I think it's best just to show you an example. So imagine you have a block that has a mass of 42.7 kilograms. The block is broken into 3 identical pieces. What is the mass of each block? Well, it's not too difficult. If we know they're identical, then we can just take the 42.7 kilograms. And again, I apologize for my sloppy handwriting. I'm hoping I will get better as the semester goes along. And I divide that by 3, and that's going to give me 14.233333333, and that'll keep going forever. All right, so my calculator is going to show all of these digits. So does that mean they're all significant? The answer is no, they're not significant. One way I see people write this is at 14.23 with a bar over it, and that's fine. That's a common practice in math to show a repeating pattern of numbers. But is the 3 even significant in this case? Turns out, no, it is not. So there's some rules for determining significant figures when doing math on the numbers. The rule in this case would say that because I did division, I need to track the original number of significant figures, which was 3 sig figs. So my answer, let's cross that one out, should actually be reported as 14.2. Of course, I have kilograms right there. All right, so what are these rules for tracking figs and for dealing with spurious digits? Again, just because your calculator gives you a bunch of numbers doesn't mean they actually have any significance. So here's the rules. If you multiply or divide, then you track sig figs. If you add or subtract, it turns out you don't watch sig figs, you watch decimal places. So you track the lowest number of decimal places in your addition or subtraction. And if you multiply numbers by an exact number, for example, you double it or you cut it into thirds, those are considered exacts, then you actually don't do anything. You just, you don't change anything in that case. This actually can be a lot of effort when you're doing a lot of math. And in this class, you're going to do a lot of math. So I'm actually going to let you off the hook a little bit. I'm not going to expect that you do this every time you go through a calculation. There's already going to be plenty of other things to worry about in your math, and I just don't want to overwhelm you. So here's going to be my rule for this class. This isn't a general rule. You shouldn't memorize this as a thing that everybody does in science. This is just this class. Okay, in this class, what I'm going to suggest is that every time you do a calculation, you keep 4 or 5 digits. Okay, even if your calculator gives you 15, you keep 4 or 5. Now, if it only gives you 2, then you can go ahead and keep 2, but if it gives you more, try to keep at least 4. All right, that's for intermediate values. Okay, these are calculations that you do before you get to the final answer. So when you get to the end and you have a final answer that you want to report, you're going to put it into homework or circle it on your exam. Then go ahead and round your final answer to 3 sig figs. And I'll go ahead and accept that as good enough for our purposes in this class. That's just because there's too much to worry about besides sig figs that I don't want to make that our primary focus. Okay, now I do need to emphasize again, you only round to 3 for your final answers. There's a lot of bad habits that I see where you'll do a calculation and you round to 1 or 2 digits, and then that results in what's called round-off error, where your final answer will be off by a certain percentage from what it should be because you just rounded too early. We're going to move on to a new subject. This is known as dimensional analysis. So another way of saying dimensional analysis is tracking units. So here's an example. John's car was at rest at a stoplight. When the light turned green, he sped up to 20 meters per second over a distance of 50 meters in 5 seconds. What was his average acceleration? For this video, don't worry about how to calculate acceleration. We'll talk plenty about that in the next video. For now, I just want to discuss the concept of dimensional analysis. So here's an example of something I see in a lot of quizzes and exams. There's some numbers that were given in the problem, some math was done, a result is given, and then the unit was thrown in as kind of an afterthought. And even if the student didn't know how to calculate acceleration, and as a hint, the student did not, but even in that case, the student really should have known that this was not the right answer. Okay, the way the student should have known is by dimensional analysis or tracking units. So let's look at the values that were used, 50 and 5. Okay, the 50 was actually a meter, and the 5 was a second. So when you do the math, you shouldn't leave out the units. You treat the units as if they're symbols in your algebra. So you almost treat them as if they were variables. They're not variables, but you would treat them in that way as if they were like x's and y's. So in this case, I'm left with 10 meters per second. Meters per second is not meters per second squared. So regardless, this is not a correct answer no matter what I say. By paying attention to the units, you can check whether you're even in the right dimension. If you're not, then it doesn't matter what your number is, it's going to be wrong. There's another way that tracking units is useful. Let's say you don't know how to calculate acceleration. You can at least get a close idea or an educated guess by just paying attention to the units. So in this case, we know that we need meters per second squared, which is going to be some sort of distance, because that's what meters represents, and it's going to be some sort of time squared. Okay, the other way you could think of it is meters per second squared is meters per second per second. Okay, in this case, this is an attractive one because we have values that match that. We have 20 meters per second and 5 seconds. Okay, and we don't have to worry about squaring anything or anything like that. Well, it turns out that this is the right way because it's asking for average. So our acceleration would be 4 meters per second squared. Sorry, technical difficulties. All right, now I should warn you that doing dimensional analysis to solve for a numeric answer can sometimes work, but it doesn't always work. It works in this case simply because I was asking for average acceleration. Any more complicated problems, this wouldn't have given you the right answer, but it gives you an idea of the power of tracking units. Here's another example. Let's say a bunch of work was done and we ended up with an answer that looked like this. Okay, first of all, you would never report this as your final answer because it's not in its simplest form. You should always try to simplify if possible. The problem with simplifying in this case is that you have a bunch of units that don't match up. So we have distance in feet and then centimeters cubed. We have time in seconds and hours and mass in grams and kilograms. So in order to simplify, because this is just one big multiplication problem, it is actually okay. You can simplify feet and centimeters even though they're not, this is feet and not cubes. Numerically, you can simplify all that down. But you would have to be in terms of centimeters or feet, or kilograms or grams. You have to have them, all of the types of quantities in the same dimension. That's going to take you a lot of work. You're going to have to go through and do a unit conversion on each one of those. Before you worry about though, there's something you should check to save yourself a little time. Do you know that this is even dimensionally consistent with speed? When I say dimensions, I'm talking about, for example, length. Length would be a dimension. In this case, you can treat all lengths as having a dimension of L. And it would be like our unit. All mass would be a dimension of M for our unit, and time would be T. When you're tracking dimensions, you don't care about the numbers, you just care about the dimensions. So let me give an example. I know that speed has dimensions of distance over time. Notice, I'm not saying speed is equal to distance over time. In some simple cases it is, but in general it's not. But in terms of the dimension, it is distance, so I'll call that length, over time, so I'll call that t. So my dimensional units would be L over t. So for dimensional analysis of this ugly looking problem, the nice thing is we're going to ignore all the numbers and the fact that they're different units and just look at what dimension was given. So if I do that, this is what ends up. So kilograms is a mass, centimeters cubed is just length cubed, seconds is time. In the bottom, hours squared becomes just time squared, feet, length, mass, dimensions of m. After I do some simplification, now that simplification is pretty easy. It simplifies down to length squared over time. This is not equal to each other. Length over time, length squared over time. So I know that this answer is not dimensionally consistent, so there's no point in wasting time doing all the conversions. It's going to be wrong no matter how much effort I put into it from this point. This is an example of how tracking units or dimensions can help you assess your problems and can correct a lot of missed problems. It's very useful in exams specifically. Okay, we're almost done. Go through just a couple more examples. So here's two random equations that I totally made up. They represent the volume for an unknown object. Only one of them is correct. How would you figure out which one's correct? I'll give you a few seconds to think about it. I won't wait too long because without more information, there's really not a good way to answer this. So let me give you a little bit more information. So here is the dimension or the represented quantity of each symbol. Notice here that I'm using the dimension rather than the specific unit. Down here, this is pi, related to circles and circumferences and things like that. So pi is actually just a number. It's not a variable or another symbol in this case. So let's do some dimensional analysis. I'll go ahead and substitute all the dimensions into this first equation here. And the thing I love about dimensional analysis is you don't care about the numbers, you only care about any units or dimension that's being represented. So in this case, that relation simplifies down to this. Notice that 3 pi squared is not there because it's dimensionless. There's no dimension here. Pi, technically, if degrees or radians, I should point out, degrees or radians is technically not a dimension that we track. Okay, after some simplification, I end up with L cubed is equal to L cubed plus L cubed over T. Hopefully your intuition tells you that this result is absolutely not correct. Okay, a rule that you should pay attention to this semester is that you cannot add or subtract numbers with different units. Never, ever, ever can you do this. So this answer is wrong always. Let's look at the second. Again, notice that I've ignored anything that doesn't have a dimension after simplification. Now, every term in my addition and equality has the same dimension. So dimensionally, this is at least consistent. So I can say that based on that information, this one should be correct. Now, that doesn't necessarily mean it's 100% correct. It's what we call dimensionally consistent. Maybe that's a better way of saying it. So this answer is dimensionally consistent where this answer is not. All right, one more example to wrap up dimensional analysis. Here's a question. Like the last problem, this would be hard to answer without some more information. So let me give you a little bit of information and see if that changes your prediction. All right, well, hopefully you recognize that the answer is no, this would not be a correct relationship. Okay, why is this not correct? Let's go through some dimensional analysis. So if x has dimensions of position, that's a distance value, it would be represented by meters or centimeters, something like that. Then what I'm saying is that I have sine of length. And if you don't know, the argument inside any trig function, the argument is this, anything inside the parentheses. The argument must be dimensionless or else the sine function won't accept it. Now what about radians and degrees? I kind of hinted at that before. Technically speaking, radians, degrees aren't units. They're what we call pseudo-units. We use them to help us track angles, but they're not technically a unit. They're a ratio, which is a unitless value. Okay, so if x was a position, then the answer is no, this would not be a correct answer. Let's consider a different case. What if x is an angle and y is a position measurement? Well, in that case, I have sine of no dimensions, so I can just call that maybe 1 in dimensional analysis because there's no dimension. So the trig function isn't giving me any problems. Angle works just fine inside a sine function. The issue, though, is y is equal to that. Okay, and y is supposed to be a position, so that should give me a dimension of length, but sine by itself is dimensionless. So how can you have a dimensionless value give you a dimension? The answer is you can't. So no, this would not be correct if this was the situation. Last example. What if x is an angle and y is a unitless value? Well, that works out just fine. Because in terms of dimensions, I'm essentially saying 1 is equal to 1. And that works just fine. So finally, we have a yes, at least as far as dimensional analysis goes, that could be a right answer. I should clarify again that it's not a 100% guarantee, but at least it's dimensionally consistent. All right, if you have any questions, further questions, please let me know about dimensional analysis. All right, we're going to wrap up this section. This is all from chapter 1 in your textbook. I did want to mention really quick that there's a short question. There's one question on homework that discusses percent uncertainty. I'm actually not going to cover that with you. Some of you may know it already. If you don't, there's a small section in the textbook in chapter 1. There's only like 2 paragraphs. There's an example in there that covers percent uncertainty. I'm going to let you go ahead and read it because I want to emphasize that you really should be reading the book. If you're not reading the book, you're missing out on extra opportunity to learn. And if you're not happy with your grade and you're not reading, then those two are related. This is the end of the material from chapter 1. This was the second part of the chapter. let me know if you have any questions.